Hi friends. Welcome to Content Factory. Today I am talking about compass. A compass is a device that shows the cardinal directions used for navigation and geographic orientation. It commonly consists of a magnetized needle or other element, such as a compass card or compass rose, which can pivot to align itself with magnetic north. Other methods may be used, including gyroscopes, magnetometers, and GPS receivers. Compasses often show angles in degrees. North corresponds to 0 degree, and the angles increase clockwise, so east is 90 degree, south is 180 degree, and west is 270 degree. These numbers allow the compass to show azimuths or bearings which are commonly stated in degrees. If local variation between magnetic north and true north is known, then direction of magnetic north also gives direction of true north. Among the four great inventions, the magnetic compass was first invented as a device for divination as early as the Chinese Han Dynasty, and later adopted for navigation by the Song Dynasty Chinese during the 11th century. The first usage of a compass recorded in Western Europe and the Islamic world occurred around 1190. The magnetic compass is the most familiar compass type. It functions as a pointer to magnetic north, the local magnetic meridian, because the magnetized needle at its heart aligns itself with the horizontal component of the Earth's magnetic field. The magnetic field exerts a torque on the needle, pulling the north end or pole of the needle approximately toward the Earth's north magnetic pole, and pulling the other toward the Earth's south magnetic pole. The needle is mounted on a low-friction pivot point. In better compasses, a jewel bearing, so it can turn easily. When the compass is held level, the needle turns until, after a few seconds to allow oscillations to die out, it settles into its equilibrium orientation. In navigation, directions on maps are usually expressed with reference to geographical or true north, the direction toward the geographical North Pole, the rotation axis of the Earth. Depending on where the compass is located on the surface of the Earth, the angle between true north and magnetic north, called magnetic declination, can vary widely with geographic location. The local magnetic declination is given on most maps, to allow the map to be oriented with a compass parallel to true north. The locations of the Earth's magnetic poles slowly change with time, which is referred to as geomagnetic secular variation. The effect of this means a map with the latest declination information should be used. Some magnetic compasses include means to manually compensate for the magnetic declination, so that the compass shows true directions. There are other ways to find north than the use of magnetism, and from a navigational point of view a total of 7 possible ways exist. 2 sensors that use 2 of the remaining 6 principles are often also called compasses, the gyrocompass and GPS compass. The first compasses in ancient Han Dynasty China were made of lodestone, a naturally magnetized, or of iron. Later compasses were made of iron needles, magnetized by striking them with a lodestone, which appeared in China by 1088 during the Song Dynasty, as described by Shenhua. Dry compasses began to appear around 1300 in medieval Europe and the Islamic world. This was supplanted in the early 20th century by the liquid-filled magnetic compass. Modern compasses usually use a magnetized needle or dial inside a capsule completely filled with a liquid, while older designs commonly incorporated a flexible rubber diaphragm or airspace inside the capsule to allow for volume changes caused by temperature or altitude. Some modern liquid compasses use smaller housings and/or flexible capsule materials to accomplish the same result. The liquid inside the capsule serves to damp the movement of the needle, reducing oscillation time and increasing stability. Key points on the compass, including the north end of the needle, are often marked with phosphorescent, photoluminescent, or self-luminous materials, to enable the compass to be read at night or in poor light. As the compass fill liquid is non-compressible under pressure, many ordinary liquid-filled compasses will operate accurately underwater to considerable depths. Many modern compasses incorporate a baseplate and protractor tool, and are referred to variously as orienteering, baseplate, map compass, or protractor designs. This type of compass uses a separate magnetized needle inside a rotating capsule, an orienting box or gate for aligning the needle with magnetic north, a transparent base containing map orienting lines, and a bezel, outer dial, marked in degrees or other units of angular measurement. The capsule is mounted in a transparent baseplate, containing a direction of travel indicator for use in taking bearings directly from a map. A magnetic compass points to magnetic North Pole, which is approximately 1,000 miles from the true geographic North Pole. A magnetic compass's user can determine true north by finding the magnetic north and then correcting for variation and deviation. Variation is defined as the angle between the direction of true north and the direction of the meridian between the magnetic poles. Variation values for most of the oceans had been calculated and published by 1914. Deviation refers to the response of the compass to local magnetic fields caused by the presence of iron and electric currents. One can partly compensate for these by careful location of the compass and the placement of compensating magnets under the compass itself. Mariners have long known that these measures do not completely cancel deviation, hence, they performed an additional step by measuring the compass bearing of a landmark with a known magnetic bearing. They then pointed their ship to the next compass point and measured again, graphing their results. In this way, correction tables could be created, which would be consulted when compasses were used when traveling in those locations. GPS receivers using two or more antennae mounted separately and blending the data with an inertial motion unit can now achieve 0.02 degree in heading accuracy and have startup times in seconds rather than hours for gyrocompass systems. The devices accurately determine the positions of the antennae on the Earth, from which the cardinal directions can be calculated. Manufactured primarily for maritime and aviation applications, they can also detect pitch and roll of ships. Small, portable GPS receivers with only a single antenna can also determine directions if they are being moved, even if only at walking pace. By accurately determining its position on the Earth at times a few seconds apart, the device can calculate its speed and the true bearing, relative to true north, of its direction of motion. Frequently, it is preferable to measure the direction in which a vehicle is actually moving, rather than its heading, the direction in which its nose is pointing. These directions may be different if there is a crosswind or tidal current. Subscribe this channel to get more informative videos.